Hello everyone, my name is Wang. It's a pleasure to be here, and I will introduce our work FraudWhistler, a resilient, robust, and plug-and-play adversary example detection method for speaker recognition. To start, let me provide some background. Speaker recognition is an automatic technique designed to answer the question who is speaking. In the real world, it has been widely applied across various domains, such as personalized services, digital forensics, and financial transactions. However, there is a significant problem. Deep learning-based SR systems are vulnerable to adversary example attacks. Imagine an adversary malware who is not an authorized user of an SR system. Under normal circumstances, malware's voice would be correctly recognized by the system, and he would fail the verification process. However, if malware adds a subtle noise to his voice, he can now deceive the system into recognizing him as Bob, successfully bypassing the verification. To human listeners, the voice sample would still sound like malware's. This scenario illustrates a classic adversary example attack. So, to mitigate adversary example attacks, various defenses have been proposed, which can be categorized into three types. The first line focuses on enhancing the robustness of SR systems by retraining the models. The second line is designed to purify the input audio by removing adversary perturbations. And the third line seeks to detect adversary examples using binary classifiers. However, these methods are all limited in scope, as they rely on training procedures based on specific pre-assumed attack algorithms. As a result, they are impractical in real-world scenarios. So, to address this issue, we proposed a detection method that leverages an intrinsic characteristic of adversary example. Let me introduce this characteristic. In a normal scenario, Bob's voice is correctly recognized as Bob's by the SR system. Malware, however, can use an adversary example to be misclassified as Bob. Now, let's introduce an audio distortion module. For Bob, even a distorted voice sample would still be recognized as his, because SR systems are initially designed to be robust against all kinds of audio distortions. However, this situation is different for adversary examples. The carefully crafted noise that enables the attack is usually subtle and can be easily disrupted, causing the attack to fail. So this indicates that the model predictions are unstable for adversary examples, while they remain stable for benign samples. To leverage this characteristic, we face several challenges. First, how to quantify this instability of model predictions. Second, how to evaluate a specific audio distortion technique. And third, how to effectively combine multiple audio distortions. To quantify the instability of model predictions, let's revise the attack scenario again. Normally, the model prediction for an SR system not only contains the output label, but also similarity score. Suppose we have an audio sample X and a distortion function D. This gives us two similarity scores. And actually, it's straightforward to say that the difference between these scores can actually reflect the instability of model predictions. Therefore, we define a difference score function to quantify this instability. The second challenge is how to evaluate and compare different distortion techniques, because there are many of them. Here, we consider two types of original audio samples, benign sample X and adversary example X prime. Then we get ds of x and ds of x prime. For a given distortion, if the distributions of these two values are distinguishable, then it should be feasible to identify adversary examples from benign ones. Thus, we define a distinguishable difference score function as an efficiency metric for a distortion technique. We also introduce an extra time cost metric to evaluate additional running effort brought by the distortions. Based on these metrics, we evaluate three types of audio distortions: signal processing, audio augmentation, and audio reconstruction. And we can see that some distortions are actually more effective. So now we have evaluated and compared different distortions. The third challenge is that how can we effectively combine them? To explore this question, we employ different combinations of distortion techniques to classify the benign samples and adversary examples and realize the results using TSA method. We found that more distortion techniques contribute to creating more accurate and simpler decision boundary, and more parameter settings for one specific distortion also improve the classification results. So based on the preliminary study, we propose FraudWhistler, which consists of a voice destructor module and a decision maker module. In the decision maker module, we only use the features extracted from benign samples to train a one-class classifier. So FraudWhistler are independent from any specific attack algorithm. So now the question is, how does FraudWhistler perform? We first evaluate FraudWhistler against different attack algorithms. In our experiment, we employ 5 algorithms and define 3 evaluation metrics: detection accuracy on adversary examples, accuracy on benign examples, and robust accuracy on adversary examples. The overall performance are shown in this table. We can see that FraudWhistler achieves the highest detection accuracy and robust accuracy and only induces a minor degradation of accuracy on benign examples. We then evaluate FraudWhistler in physical world. We use a speaker to play the adversary example and use a device to record it. At the same time, we use another device to play white noise to control the background noise level. Here we can see that FraudWhistler always achieves the highest robust accuracy in different distance settings. Regarding background noise levels, FraudWhistler consistently outperforms other methods when the noise is relatively quiet. As the noise intensity increases, even SR systems without any defense can achieve a robust accuracy above 80%. So at this time, the defense doesn't matter. This figure shows that FraudWhistler consistently achieves the best performance across various types of recording devices. So next, we evaluate FraudWhistler under adaptive settings. In this setting, the adversary is aware of the existence and the details of FraudWhistler. So he can accordingly modify the objective function to generate more powerful adversary examples. This figure shows that when the perturbation budget increases, the attack success rate indeed reaches higher, which means that FraudWhistler may be susceptible to adaptive attacks. However, we can also see that the signal-to-noise ratio also decreases. When the attack success rate reaches about 75%, the SNR drops below 15 dB. In fact, maintaining the imperceptibility for adversary examples is crucial in practical scenarios. For this reason, we conduct another audibility study. This figure shows that though FraudWhistler achieves worse accuracy when the perturbation budget increases, the human ears could identify adversary examples more accurately This indicates that although the adversary could improve the attack success rate with higher perturbation, the impact on imperceptibility would render them failed to spoof human ears. In the worst case, the attacks are identified by either human or FraudWhistler with an accuracy of 84%, which demonstrates that FraudWhistler can force the adversarial example to either fail to bypass the SR system or become noticeable to human ears. So here comes a summary. In this work, we present a study evaluating a wide range of audio distortion techniques and proposed an adversary example detection method based on that. The experimental results show that FraudWhistler not only achieves resilient performance against various attack algorithms, but also are robust in complex, realistic conditions and effective even under adaptive attack settings. So thanks for listening. Any questions?